Alrighty, let's talk about lemmas. Okay, so we are all here because we're all computer scientists, specifically those that love programming languages. And so I feel like it's safe to assume we've all written a program before, and that means it's probably also safe to assume that we have written a program that does not work. And everyone's familiar, and maybe not everyone, but most people are familiar with formal methods, specifically with interactive theorem provers like Lean and Rocq that are getting a lot of traction these days. And these tools let you formally verify your software, so you're able to prove properties about your programs or mathematics or other systems that you care to specify. But this still begs the question as to why we still have bugs in software. And it's because these tools aren't necessarily easy to use all the time. And there's a burden, whether it's time or difficulty, to verify your stuff in them. And so we're going to walk through an example of trying to verify selection sort. And this comes from the Verified Functional Algorithms textbook and the Software Foundation sequence. And the main property you might want to verify about your selection sort, or any sort for that matter, is that it correctly sorts your list. And the Verified Functional Algorithms textbook, along with the other Software Foundations textbooks, are in Rocq, and they provide you with a sequence of lemmas to prove.
Your mic is, when you face that way, your mic is so comfortable. Yeah, so like that.
Keep it like that? Okay, hold on. Can I hold it? Okay, I'm just gonna hold it. I'm gonna hold it then. Okay, where was I? Okay, so if you want to prove that your list is correctly sorted, in this case, you might want to prove that this following property, that if you have an element n and it's less than every element in your list, and then you're able to correctly sort that list using your selection sort, then if you put that element at the front of your list, then the list will remain sorted. And it's important to note in this context that LEAL is a proposition, an inductive proposition, that is defined in conjunction with your list, and and you want to reason about how this proposition works in comparison with your property you care about. And when you're trying to prove this property, you need to prove it, and there's additional lemmas that might help you prove it. Okay. So when you're using an interactive theorem prover, you do it tactic by tactic. And whether you're doing it manually or you're using some kind of automated tool, it's doing a next tactic prediction. And often these tools, or you yourself as the prover, have access to prior context. And specifically, we're talking about lemmas. And so often these techniques will consider the helper lemmas, and the specific helper lemma that's useful in this context is the following, which states that if you have an element that is less than all elements in a list, and you know that another element is within that list, then the element that is less than all the other elements will be less than the element in that list, which is on the bottom there. And the Verified Functional Algorithms textbook provides you with this lemma, as well as others that are useful in completing your proof. But this begs the question of, if you're verifying your own software that you've created, or anything else for that matter, then what happens when you don't have access to these lemmas and you might get stuck, whether it's you proving it yourself, or especially an automatic tool that's used to having access to prior context in a lot of its training. And so this is where we get our problem statement from. How can we determine useful helper lemmas that help us complete our proofs from scratch? And so we're going to define the problem of directed lemma synthesis. And there's a variety of different techniques that you can use to come up with lemmas or other useful properties. But when we say directed lemma synthesis, we're referring to the context where you have an incomplete or a partial proof, where you might be stuck, and you don't know how to continue, whether, again, it's you or some kind of automation technique. And the result is a list of potentially useful lemmas that can be used to help you complete or make progress in the proof at your given point. And so we created a Rocq tactic called Dilemma that implements our approach. And there have been prior attempts and successful attempts at lemma synthesis. And so I'm going to talk a little bit about what makes ours different. So if you remember from previous slides, this is the helper lemma that is provided within the scope of the Verified Functional Algorithms textbook that's used to help complete the proof that we care about. And you'll notice that this lemma includes implicants and is an implication. And so we're going to generalize this and say this is an implication lemma, just meaning that it has an implication in it. And a lot of prior lemma synthesis work targets atomic lemmas. So these are things that will be useful in rewrites or direct application. But for our context, and in a lot of contexts when you're writing lemmas, you often need implications. And so for that reason, we're targeting implication lemmas rather than atomic lemmas. And there also has been prior work that will yield atomic or implication lemmas, but these approaches are kind of restricted in how they search the space. They're specifically heuristically applying rewrite rules, which will only yield things that are constrained by equality. And so the search space of implicants is a little bit constricted. And so for that reason, we're going to reduce our problem to a data-driven program synthesis problem, which lets you increase expressivity over the types of terms and propositions that you're searching for. We had evaluated our tool on 226 locations in the verified functional algorithms textbook, and what this means is that we had completed the proofs, someone had completed the proofs, and wherever there was a helper lemma used, we checked if our tool could find that helper lemma. And in 43% of the places we did either find an exact match or a similarly useful lemma, and the exact characterization of that is within our paper. And so the question is, how exactly do we do that? And so we're starting with our implication target. So we know we're targeting an implication lemma. And specifically, this is the one that we're looking at in this example. So LEAL of n in L, so n is less than all elements in L, and the fact that x is in the list L means that n will be less than or equal to L. And so for those who are not familiar with an interactive theorem prover, which leverages tactics, this is kind of what your interactive setting of the proof looks like. The top 4 lines are going to be your assumptions, so things you can take for granted or assume to be true in your proof. And the bottom line is the goal that you want to prove. And so if we're targeting a lemma that is going to be applied in this instance, it's kind of natural that you'd want your goal to match the result of your implication so you can directly apply it. And in this case, you'll see that that's how the lemma was used. And so we're able to get our goal or our result of our implication from the goal of our lemma. And then the question comes, how exactly do we find the implicant? So what are the preconditions or the guards on this goal? And a natural place to look is the assumptions. These are things that you can assume to be true. But in this case, you'll see that there's quite a bit of assumptions, and not all of them are always necessary. And oftentimes, good lemmas are more refined. And so it's kind of specifying the exact properties that you need in order to complete the lemma. And so that's our challenge. We have too many assumptions. How do we actually determine which ones are relevant to what we're trying to prove? And so our goal, with that being said, is to determine a minimum set of assumptions which imply the goal. And as I alluded to a little bit before, we're going to take a data-driven approach. And so before I describe that, it's important that we understand what exactly I mean by data. And in this context, data is a sample valuation over all the variables, specifically that falsifies the goal. So an example of this would be something like this, where you have values associated with each of the variables. And you'll see here, if you just plug the values through, that n is in fact not less than 2. And so we can also see how this example performs on the assumptions. And if we want the proof state to remain valid, either the goal has to be true, which is not the case, which means that there has to be some assumption that we are considering that will be false. And so in this case, it's the first assumption. And so we keep this assumption in our set, and you'll see that it is one of the implicants in our lemma that we're targeting. And so we repeat this process of ensuring that all the sample valuations that falsify the goal are somewhere in our assumptions, or falsifying an assumption. And we repeat this until based off of our type generations, or type-based generations, don't have any counterexamples on the goal that are not falsified by an assumption. And so we're left with this. And so if you look at this lemma here, this is actually a useful lemma. We've reduced our assumptions to be the ones that are relevant to our goal. And so we can return this, we can consider this and give this to the user. But oftentimes we want to do something a little bit more, and specifically we know we're targeting this lemma here. And it's pretty similar, but you'll notice that one of the assumptions is actually a bit too strong for our case. And so this will actually be the bottom lemma will be a stronger lemma than the top lemma. because one of the assumptions becomes weaker, which is hard to think about, but if your assumption becomes weaker, your overall lemma becomes stronger. And so now we're targeting weakening this assumption. And this is where the data-driven synthesis comes in. We want to reduce this problem of weakening an implicant to a data-driven synthesis problem. And we do this by isolating sets of positive and negative examples. And in this context, an example is similar in the last context. It's different valuations of every variable in the proof step. And we're in charge of splitting apart these examples into positive and negative ones, where the positive ones should be true on the resulting result of our synthesis, and the negative ones should make that result false. And so effectively what this does is this searches for a term that is implied by the assumption. In this case, we end up finding that X is an L. And if we look at the bottom, it's kind of maybe clear to see that if you sort a list L and it's equal to a list that starts with X, then X is in fact an L. And so this itself is also a lemma. And when we plug that value back in, we end up with our target lemma. But we were able to get it not by using our brains like the people of software foundations, but by using a tool that performed data-driven synthesis from the goal state. And so our overall approach has two passes that go through it. We just described the top one. The bottom one is a case where your proof state is a little bit different. And we don't have time to go over that, but it uses a similar-ish technique. Instead of weakening assumptions, you're inferring ones that are needed. You can see the paper for that. Directions for future work would include first improving the actual lemma synthesis. One big area that we'd want to look at is incorporating stronger forward reasoning. So we're targeting more backwards reasoning where your result is a goal and you're trying to get that. One forward reasoning approach would be to work forward from your assumptions and prioritize that. Additionally, we're all aware everyone likes to use LLMs for things, and so it might be beneficial to incorporate this tool with LLMs to help kind of determine, to synthesize helper lemmas as you go, or even further determining when a helper lemma is actually needed. And in summary, we have proposed a data-driven synthesis technique for implication lemmas and implemented it in a Rocq tactic and evaluated it on some benchmarks. And going forward, I think this area is really interesting, and I think that it's worth thinking about how you can deconstruct proofs to aid in either proof automation or creating tools that help users actually work through their proofs in a way that makes more sense as opposed to just hacking at it. Thank you for listening. If you have any questions, comments, or discussion, feel free to reach out, and I can take any questions anyone might have. Sorry about the mic.
We have time for one question.
Yeah, thanks for the great talk. I'm wondering if in the current proof state, if we have quantifiers, like existential quantification, does your approach still work or not?
The approach, I think, conceptually works. In terms of the implementation, we run into some issues, so that would be included in the category of improving the implementation. Like, for example, we don't do function types because we weren't writing generators for function types. That's a little bit complicated. But so that would be a category where I think theoretically it would work, but in terms of like actually identifying and generalizing and instantiating examples, it would be a bit more complicated. Does that answer your question?
Thanks.
Yeah, thank you.
All right, let's thank the speaker again.